Welcome to the 1968 Nobel Prize in Physics, which went to Luis Walter Alvarez. Humorously, my dad's name was actually Luis Walter, but Imholt, so a little no relation, but I just find that interesting. Now the prize officially was for something else, but I'm going to call this one the Data and Analytics Prize, and that I think applies to the modern world in a lot of ways. So let's get to that in a minute. But this prize was for officially for his decisive contributions to elementary particle physics, and particularly for his discovery of a large number of resonance states made possible through his development of the techniques using the hydrogen bubble chamber and data analytics. Whew. Okay. That's the official prize wording. What the heck does all that mean in English? Let's get to that. Now, but let's go, let's do a little trip down memory lane first. Now, the bubble chamber, if you remember, was first demonstrated in 1952 and won the Nobel Prize for Donald Glaser in 1960. So that video is on the channel if you want to check it out. Now, also, that prize was influenced by a prize that came before that by C.T.R. Wilson with his development of the cloud chamber, which won the prize in 1927. So these guys are like standing on the shoulders of a giant, standing on the shoulder of a giant to win the prize, which is kind of cool. Now, analysis is really a large part of modern physics because with sensor technology, you can build a sensor to detect just about anything if you got enough money. That's not the problem. But how do you analyze the mounds and mounds and mounds of data coming out of it? It's like at my day job, we do data analytics, and we analyze a petabyte a week. I mean, if that's a slow week, if we're only analyzing a petabyte. So yeah, we data analytics everywhere. The amount of data the world has is far exceeding that which we could ever possibly analyze, at least with modern computing, until quantum computers come online. But he built a Nobel Prize winning project on the back of his strong background in data and analysis, which he gained during World War II. So, he wasn't like, hey, let's go build all these new techniques, let's go build all these new apparatus. He was like, hey, let's just take all the stuff we got and figure out how to analyze the data better. And that's what won him the prize. So let's take a quick look at what he learned during World War II. Now, his background and his experience was so important to this prize that it's we kind of have to go back to him getting his PhD. So he actually got it in 1936 from the University of Chicago, and he worked under a guy named Arthur Compton, who won the Nobel Prize in 1927. In 1940, he actually left there and joined the MIT Radiation Lab, which was their radar lab because radar was brand new at the time. So it was, the microwave oven, all these things were just kind of coming out of labs and heading into World War II. And he went to work for the Rad Lab at MIT, which is still there in ways, but was instrumental in designing the radar used during World War II. Uh, while he was there, he worked on a variety of projects, including an identify friend or foe beacon that's now called a transponder that's in pretty much every airplane out there. So think about it at the time, if you see a radar signature, you got a bunch of incoming airplanes, you launch yours, oh crap, they're ours, right? So you want that identify friend foe thing to be real. He worked on that. He worked on a system called Vixen, which was a method of preventing enemy submarines from knowing they were showing up on radar. Remember, he's doing all this just by taking other people's hardware and figuring out how to analyze that data better and give a feedback loop into things, so that we're using all the data we have instead of just letting data go to waste because that actually matters. Uh, he was also hugely instrumental in the data analysis sets and how to use what are still modern day ground control approach radars and how to analyze the data coming out of those. So, big guy when it comes to all the radar things. And radar, I've actually worked with radar. Analyzing radar data is relatively routine, but it's still not that simple. If you just hand somebody who's unfamiliar with it just a pile of radar data and say, "Here, analyze this," it's not as simple as you think. We've made it look routine because we poured millions of man hours into it, but it's not as simple as you would think it is. Now, after that, he went back to the University of Chicago and he worked under Fermi, Nobel Prize from 1938. He worked on some of the development of the world's first nuclear reactors before going over to Los Alamos to work with Oppenheimer on the Manhattan Project. And specifically, he worked on helping analyze data so they could better um, build the explosive lenses used for the plutonium devices. So, how do you really analyze exactly what the explosive results are to get the focus you need to build a plutonium device? That was him. He was a member of that team. He did observe the Trinity test from a B-29, again, gathering data for further analysis. He even was an observer for the Hiroshima bombing again from a B-29, not the one that dropped it, but from one called the Great Aristi or something like that. Now, but from every one of those projects, what he did was he learned new roles in how to analyze data and analyze data better, and more importantly, analyze data faster. Because if you've got tons and tons and tons of data and you can't analyze it quick enough, what good does it do you on a particular project? It's like, oh, I need a project in a week. Great, I've got 5 years worth of analysis. Call me in 5 years. It doesn't work, right? You've got to do it faster and faster. So when you deal with radar and you deal with things that are in the nuclear world, you have to be able to take data quickly over very small periods of time. You can't say, "Oh, I need 5 seconds to take an image." You need to do it really quickly. So what he did was he used all that experience to bring it back to the laboratory and build an apparatus that would take millions of photographs of what's going on inside a bubble chamber. Remember, the bubble chamber was a way to look at particles that they didn't have before. So, but what he did was now you've got this chance to take these photographs. And instead of taking a couple of photographs here and there, he was taking millions of them. Well, now that you got millions of photographs, you're not going to sit down with an individual and a slide rule and a person and figure out how to analyze millions of photos using a pen and paper. That's not going to work. You can't possibly get through them all. So what he did was he used some of those computer techniques that he learned during the war. Remember, computers are kind of in their infancy here, to build an apparatus that would actually analyze all that data very quickly by comparison to the human version of it. Now, that led him to the Nobel Prize because out of those millions of photographs that other people were seeing anyway, I mean, you see these little things in there. You're like, okay, I'm looking for this. I found that. I'm going to stop analyzing. You get all these other little things inside that image you may just disregard because the thing you were looking at's over here, and you get all this other stuff over here. You're like, I don't care. It's probably noise anyway. So what? Right. So what that did was what the speeding up process did was it enabled him to discover entire new families of particles that had never been seen. He also discovered new resonances inside these things that had never before been seen, and that led to the Nobel Prize. But it was basically just taking stuff that existed in other parts of the scientific and engineering community and applied it to this problem, and boom, out pops a Nobel Prize. But wait, there's more, as they say. He then went on after the prize to work on an X-ray project to look for unknown chambers in the Great Pyramids, which was somewhat successful. He then worked with his son, who was a geologist named Walter Alvarez, and did some data analysis that allowed them to develop the theory that dinosaurs were destroyed by the extinction event that killed the dinosaurs was as a result of a large asteroid hit. Popped another one for data analytics. Now, fast forward to the modern world, we've gotten a little bit spoiled by just saying, oh, we'll have fast computers and we don't care if the code's inefficient. Well, now what's going on is you've got sort of inefficient code. It's getting better to do data analytic work. And what we've done over time is we've just cranked the processor power up more and more and just said, let the processors do the work and we don't care. Well, now what's happening is we're gathering more data than ever before, and we don't have the computer power to really analyze everything you want. I mean, there's a ton of data out there. That's how weird it is. Ever try to search for something rare? Go to Google and start, and it could be 3 hours before you find it. And once you find it, now you've got to analyze all that information and collate all the information and work on it in your head. Well, if you're doing something for a large company, that gets even harder. So these data analytics projects become much more important in the modern sense because we have more data than ever before. And how do you simplify that? So using existing tools, he did just that. He simplified it and discovered things we didn't know. And I'm curious how much data we have out in the world that has been gathered that's got stuff in it we're just missing, right? So can we actually build better techniques to go back and analyze old data sets to show us what we didn't really fully understand? So I think we need to learn from his example and maybe say, hey, look, maybe we should try to figure out better ways to analyze stuff instead of just building bigger and better detectors. I mean, I get, the fun part of building bigger stuff, but we've got tons of data. Let's make sure we haven't missed anything in it. I think that's just as important as building better sensors. So I hope you've enjoyed this. Don't forget to click like and subscribe, and we will see you on the next video. Have a good one.